are watching session number 2 of the chapter Polymers. In first session, we discussed about the terms used in polymers, different classification of polymers and types of polymerization. In this session, I am going to discuss only about the examples. Before moving with the examples, let me recall you how to identify the two different types of polymerization. We know that one addition polymerization and one more is condensation polymerization. One very simple way is you have to see whether there is elimination of simple molecule like water or not. If there is no elimination of simple molecule like water, that belongs to addition polymerization. If there is elimination of simple molecule like water, and that belongs to condensation polymerization. One more way is you have to check the monomers. If the monomers contains carbon-carbon double bond or carbon-carbon triple bond, that belongs to addition polymerization. If the monomer contains bifunctional groups or trifunctional groups, that belongs to condensation polymerization. So after knowing this concept, we'll discuss some examples and we'll try to identify whether it is addition or condensation polymerization. And one more concept I told you already, that is in case of addition polymers, we have two different subtypes. One is homopolymers and one more is copolymers. If there is same kind of monomers are present, that belongs to homopolymers. Two different kind of monomers are present, that belongs to copolymers. We will apply these principles to these examples and will try to write the partial structure and monomer and the simplest reaction for different examples, and will try to identify what kind of polymer it is. We will discuss one by one. The first one, I am going to talk about Ldpe. Okay, Ldpe, and I hope you remember I used this particular example while explaining the classification of polymers. Based on structure, polymers can be classified into linear, branched and cross-linked, isn't it? So Ldpe is an example for a branched polymer. You try to know about that, branched polymer. And Ldpe stands for low density polyethylene. I am going to write here Ldpe stands for low density polyethylene. Low density polyethylene. We will see the monomer and partial reaction, how to write the reaction and how we can write the statement for this one. So low density polyethylene, it is the name of the polymers, and first you should know what is the monomer of this. Polyethylene, the monomer will be ethene. So how we are going to write that? CH2 double bond CH2, this will be the monomer, and large number of monomers will combine, you are going to get the polymer, we know. Therefore I should write small n number of, large number of, and of course it undergoes a kind of polymerization, and we are going to get the polymer, and that will be CH2 single bond CH2 and bracket n I am supposed to write. So the left side it continues, the right side also continues, and braces or brackets you have to write subscript n, you are supposed to write here. Double bond is converted into single bond and the valency of a carbon is satisfied, and this is the repeating unit, and n number of the same repeating unit you have. Therefore this is the way how we are supposed to represent the polymer. But this is the very simple method of writing polyethylene. But low density polyethylene means we have to apply certain conditions. And what are those conditions? You have to maintain, high temperature, and you have to maintain high pressure. These are the conditions you are supposed to maintain. And we are supposed to add a catalyst, and that we call it as any peroxide catalyst we are supposed to consider. Peroxide catalyst, that may be hydrogen peroxide or benzoic peroxide, any peroxide you are supposed to consider, and that will act as a catalyst, and the condition is high temperature and high pressure. In this case, the kind of polythene what we are going to get, and that will be branched, and therefore we call it as a low density polythene. And this will be the name of the monomer, we know that one, that will be ethene, and that will be what actually LDPE. Okay, so this is LDPE, that is the low density polythene. So this is how we are supposed to write the polymer reaction. Okay, and try to know the product side what I have written, and this we call it as the partial structure of polymer. Okay, in the examination if they ask draw or write the partial structure, you need to write only the final product or the partial structure we call it as, and this is a complete reaction of the polymer how we are supposed to write. And the question arises how to write the statement for this one. I told you already, in the statement you should mention the name of the monomer, name of the polymer, and compulsory you have to maintain the type of polymerization. And just guess what kind of polymerization this is. In this particular example, there is no elimination of simple molecule like water, and we have carbon-carbon double bond, and from the fundamental concept one can guess that this belongs to addition polymerization, and while writing the statement you are supposed to use addition polymerization. And in particular we have single kind of monomer, we have only one type of monomer, that will be ethene. Therefore, in particular this belongs to homopolymerization, and the right statement how you are supposed to write is low density polyethene is formed by homopolymerization or addition polymerization of ethene in the presence of peroxide catalyst at high temperature and high pressure. That is a statement what you are supposed to write. And this is all about the first example, that is the LDPE, which belongs to branched polymer. Similarly, we will see the next one. Second one I am moving with. Okay, and the second one here I am going to talk about Hdpe. Okay, Hdpe. I hope you can guess the actual name. That will be high density polyethylene. High density polyethylene. Okay, so that is actually Hdpe we call it as, and now you just try to recall. Okay, and where we studied the Hdpe concept. So again in the same, based on the structure, Hdpe belongs to linear polymers. We have a long and straight chain polymer. We don't have any branches or cross-linking agents in this case. So therefore Hdpe belongs to linear polymers. So how to write the monomer, how to write the polymer, what are the conditions, and what is the statement for this particular monomer and polymer, we'll see now. So Hdpe, polyethylene, and the monomer will be what actually ethene itself. So how I am supposed to write? CH2 double bond CH2, large number of monomer N, and this undergoes a kind of polymerization, and we are going to get the polymer CH2 single bond CH2, the bonds will extend, place brackets and subscript N. That is the partial structure of Hdpe, and here also the reaction is as same as the polythene, but the conditions make some properties of polythene different. That's why that belongs to high density polyethylene. Usually the low temperature is required and high pressure is required in this case of Hdpe. So just if you compare LDPE and Hdpe, based on that I have written in which case high temperature, high pressure is required, in which case low temperature and low pressure is required. In case of LDPE, peroxide catalyst we use. In case of Hdpe, one very important catalyst we are going to use, and that we call it as Zeglernata Catalyst. Zeglernata Catalyst. So Zeglernata Catalyst is used in the manufacture of Hdpe. Try to know that one. Zegler and Nata are the name of the scientists, and they got the Nobel Prize for this particular catalyst what they used, therefore this catalyst we call it as Zeglernata Catalyst, and that will be used in case of Hdpe. And out of curiosity, we'll write how actually the molecular formula of this stands for, that is C2H5 thrice of Al plus TiCl4. This is actually the formula that belongs to Zeglernata Catalyst. Triethyl aluminium and titanium tetrachloride. The composition of these two we call it as Zeglernata Catalyst. I repeat, triethyl aluminium and titanium tetrachloride. This mixture we call it as a Zeglernata Catalyst, and the Zeglernata Catalyst is used in the manufacture of Hdpe. Okay, and how to write the statement for this one? And I told you already, you need to write the monomer's name and you need to write the polymer's name. Okay, it will be better. This will be Hdpe, and now you can guess how we are supposed to write the statement for this one. Hdpe or high density polyethylene is formed by addition polymerization or homopolymerization of ethene in the presence of Zeglernata catalyst at low temperature and low pressure. That's how you are supposed to write the statement for that one. And remember, you need to know the properties of these also. So now I am going to compare the properties, or you can say the applications of LDPE and HDPE. Okay, so remember, both are tough in nature, both are chemical resistance, inert in nature. Okay, but whereas LDPE is flexible in nature, whereas HDPE is very hard and tough. Based on this property, LDPE is used in insulating electric wires. If you consider the copper wire, and you are supposed to observe the insulating material on that. Okay, that will be flexible, isn't it? And that particular material is LDPE. And Hdpe is also insulating material, but that is hard and tough, and that is not as flexible as LDPE. Therefore, in case of buckets, dustbins and pipes, we are supposed to use what actually Hdpe. So this is how the property and applications you should know. And one concept you remember, LDPE is branched polymer, Hdpe is a linear polymer. Catalyst we used is peroxide in case of LDPE and Zeglernata catalyst in case of Hdpe. And the formula of Zeglernata catalyst you need to remember, because in recent KCET examination we have this particular the formula of Zeglernata catalyst in the form of the word also you should know, triethyl aluminium and titanium tetrachloride. I told you this one, and that is used in Hdpe, and both belongs to the class of polymerization, addition polymerization, right? We'll move with the next one then. So the third example I am going to consider is polypropylene. Polypropylene, sometimes you can call it as a PP also. Okay, polypropylene, that is the name of the polymer. And now I hope you can guess what would be the monomer of polypropylene. The monomer will be propene itself. So we'll see how we can write the reaction for that. Okay, so propene, CH2 double bond CH and CH3 I am going to consider. Okay, so 3 carbons we have, and we have one double bond of propene. This is so CH3 I have written below, or you can write above, the same thing, and a large number of propene, and that will undergo the kind of polymerization. I told you that one, and we are going to get the this is the structure of polypropylene, right? So what happened actually, carbon carbon double bond has converted into carbon carbon single bond, tetravalence nature is satisfied, and this we call it as propene, and this we call it as polypropene. And now I hope you can guess what kind of polymerization is involved. No elimination of simple molecule, carbon-carbon double bond. That's why this polypropylene belongs to addition polymerization. How to write the statement? Polypropylene is formed by addition polymerization of propene, or you can say particularly homopolymerization of propene. You are supposed to consider. That is how we write, the polypropylene structure. Similarly, we'll see the next one, polypropylene. And now I am going to talk about polyvinyl chloride. Polyvinyl chloride, and the simple form we can write PVC, polyvinyl chloride. This is a synthetic polymer venom, and it is used in water pipes. Well known polymer it is, polyvinyl chloride. Okay, and now we'll write the complete reaction and the partial structure and the statement. And the polyvinyl chloride, name the monomer of polyvinyl chloride. The answer will be here itself. The monomer will be vinyl chloride. Okay, so we'll try to write the structure of vinyl chloride. Okay, vinyl chloride, almost similar we have allyl chloride, vinyl allyl, we use that frequently, isn't it? So remember, vinyl, in case of vinyl actually we have 2 carbons, in case of allyl we have 3 carbons. Of course, carbon-carbon double bond will be present in case of vinyl as well as in case of allyl, vinyl chloride, and the structure I am going to write here, CH2 double bond CHCl. So this is the structure of vinyl chloride. So carbon-carbon double bond we have, Cl I have written, therefore that we call it as the vinyl chloride. Okay, so when vinyl chloride undergoes the polymerization, okay, carbon-carbon double bond we have, one can guess this undergoes what actually addition polymerization. Particularly we have a single kind of monomer, homopolymerization, and how we are supposed to write CH2 single bond CH. The Cl I am going to write in a branched manner, and that would be the structure of a polyvinyl chloride. And try to know that one, in all the cases what we have seen, tetravalence nature of carbon should be satisfied, double bond is going to be converted into single bond here, and that would be the structure of a PVC polyvinyl chloride, and the name we are supposed to write here, and this will be vinyl chloride, and this will be polyvinyl chloride, and the kind of polymerization involved is the addition polymerization. Since there is no elimination of a simple molecule and carbon-carbon double bond is going to be involved. Okay, and how to write the statement? Polyvinyl chloride is formed by addition polymerization of vinyl chloride. That's it. Okay, and application I told you, in case of hard and tough kind of substances like water pipes and bottles, for vinyl flooring also this particular polymer polyvinyl chloride is going to be used. Okay, and we'll see some similar examples. The fifth one I am going to write. Okay, and the fifth one I am going to talk about the Orlon, and one more name we have for that one. I am going to write that also, polyacronitrile, Orlon or polyacronitrile. Okay, and we'll see what would be the structure of polyacronitrile or Orlon. And first we'll see what is the monomer of that one. Okay, so see here, polyacronitrile, the monomer will be acronitrile, and that is the one commercial name what we have. And now let me write the monomer, and I hope you can guess what would be the name of that. Okay, so just guess what would be the name of this monomer. CH2 double bond CHCl. Okay, and this is almost the same as the previous one. Okay, so this we call it as vinyl chloride, since we have Cl. So here we have Cn, and we know that one, that is cyanide. So name of this will be vinyl cyanide. Vinyl cyanide we call it as, and one more name is what actually acronitrile. Okay, so try to know that one. So vinyl cyanide, you can call it as acronitrile. Usually if we get the word called acronitrile and we don't remember quickly what would be the structure, so try to know acronitrile is nothing but a vinyl cyanide, and vinyl two carbons will be present, and vinyl cyanides here I have. And now this undergoes what actually the polymerization, okay, and here we are supposed to consider the peroxide as catalyst. Okay, sometimes we add peroxide as a catalyst, and we are going to get the structure of the polymer, that is CH2CN, and CN will be branched, okay, and the brackets I will write and subscript N I will write. The same kind Cl will be below here, and Cn I am going to write it below, and this I call it as what actually polyvinyl cyanide. Okay, you can call it as polyvinyl cyanide. You can call it as polyvinyl cyanide. Similarly, vinyl chloride, polyvinyl chloride, vinyl cyanide, polyvinyl cyanide, and you can call it as what actually P polyacronitrile. See, polyacronitrile, the short form you can write PAN, that stands for polyacronitrile. Okay, and that is also addition polymer, and we came to know that here again we have carbon carbon double bond, there is no elimination of simple molecule like water, and one can guess that belongs to the addition polymer. The statement polyacronitrile is formed by addition polymerization of vinyl cyanide or acronitrile in presence of peroxide. The statement will be same. Okay, and that is about Orlon. And now you try to know Orlon, the word I hope you are quite familiar. This is the alternative for the wool. Alternative for the wool, you can say. So wool, in the place of wool, nowadays recently the commercial chemically prepared polymer Orlon is going to be used. One more we'll see, 6th one, and that will be Teflon. We'll see what about that one, Teflon, and that we call it as polytetrafluoroethene. Polytetrafluoroethene. Okay, polytetrafluoroethene is the name, that is nothing but Teflon. We'll see what would be the monomer. Polytetrafluoroethene, the monomer will be tetrafluoroethene. So how I supposed to write? CF2 double bond CF2. See here, 4 fluorine we have, tetrafluoroethene, and this is a monomer N, and that undergoes what actually a kind of polymerization, and we are supposed to add actually peroxide, and I hope you can maintain the high pressure condition here. Okay, and it is very simple, it is as similar as the ethene, and we are going to get what actually CF2 single bond CF2, and bonds you extend, put brackets and subscript write N. Okay, and this we call it as what actually the Teflon. Okay, and this is nothing but tetrafluoroethene. Okay, and how we are supposed to write the statement? Teflon is formed by addition polymerization or particularly homopolymerization of tetrafluoroethene in presence of peroxide at high pressure, and that is how we are supposed to write the statement for Teflon. And I hope you quite familiar with the word Teflon. Teflon is quite resistant to the corrosion, and that is usually coated on iron articles, or if you want non-stick kitchenwares, if you consider, the surface is going to be coated with Teflon, that is quite all resistance, corrosion resistance you can say, and that is how we are supposed to write the properties and application of that. Okay, so all these polymers what I have explained, that is LDPE, HDPE, polypropylene, polyvinyl chloride, Orlon and Teflon, actually all these if you consider, and all these belongs to addition polymerization, particularly homopolymerization. Similarly, we'll see some other examples. 7th one I am going to talk is polystyrene. Polystyrene. So how polystyrene is going to be formed? So see here, benzene ring with C double bond C, CH2 and H, and that is the monomer of polystyrene, okay, and the name will be styrene, right? And when it undergoes addition polymerization, since only one type of monomer we have, we can say undergoes homopolymerization, and we are going to get the polymer as C, single bond C, and here it continues CH and CH2, okay, and we are supposed to place the braces and subscript N you are supposed to consider. If this is styrene and after polymerization we are going to get what actually polystyrene. That is how we are going to write the structure of polystyrene, and the statement would be polystyrene is formed by addition polymerization or homopolymerization of styrene. And some applications, and these are going to be used in the manufacture of materials which are going to be used in radio, TV, like that. So that is how the applications of polystyrene we can consider. Some other example. So this is actually homopolymerization example I told you, and we will discuss one more type of addition polymerization, and that will be quite important one, Buna-S. Buna-S is the polymer what I consider, and I explained this already while explaining the meaning of copolymerization. I am going to repeat that, okay. So Buna-S, I told you already, Buna-S is the type of addition polymerization, you know that, and Buna-S is the type of copolymer. Means in Buna-S we have two different kind of monomers. So what are those? If you know the name very well and you can guess what would be the name of the two monomers. Here Bu stands for 1,3-betadiene. I am going to write here 1,3-butadiene. Okay, and S stands for styrene. We used earlier styrene, the same thing, 1,3-betadiene and styrene, and Na stands for the sodium catalyst, 1,3-betadiene, and I told you already we have but, that is 4 carbons, ene, carbon carbon double bond, dienes, 2 carbon carbon double bonds, and the position is 1 and 3. Okay, so we will complete the structure. Okay, here we get a single bond, CH and the CH2, large number of the monomer. Styrene, okay, and I told you now how to write the structure of styrene, C double bond C, here it is H2 and here it is H and N, large amount of, and that will be in the presence of what actually sodium catalyst, as the name indicates. Here Na stands for sodium catalyst, and here you can mention what kind of polymerization, that will be copolymerization. You can mention either in the reaction itself or in the form of a statement. Okay, and since two different kind of monomers we have, and that belongs to copolymerization, we know, and you should know how to join and how to write the polymer structure, and the structure what I am drawing, and that we call it as the partial structure, I told you already, and left side and right side the bond continues, you know that well, and double bond, single bond, they used to switch. This is the way how I told you to remember in a very simple way. So CH2, left side the bond extends, okay, we have a double bond, I am going to convert it into single bond, okay, and the CH, single bond and double bond, we have CH2, and this carbon is going to be joined or linked with the carbon of styrene, okay, and we have again CH and single bond CH2, the bond exists, and to this carbon we have a benzene ring, we can write above or below, okay, and that would be the structure of what actually Buna-S. And just check whether the valency of carbon is going to be balanced or not, okay, and that would be the perfect structure what I can draw, and this I call it as what actually this will be Buna-S, Buna hyphen capital S you are supposed to write. And the statement I explained you already, Buna S is formed by copolymerization of 1,3-butadiene and styrene in the presence of sodium catalyst. Okay, and this is how you are supposed to write in equation form. And the statement I told you, if they ask only the partial structure, you need to remember the complete partial structure of that. And if you don't know how to remember the partial structure of this particular Buna-S, there is no big deal in that one. Within a fraction of seconds we can write the monomers and we can get what kind of polymer it is, and that belongs to addition polymer, particularly copolymer, since we have two different kind of monomers. And that is about the polystyrene, and one more is Buna-S. So before moving with the 9th example, I am going to explain some points. Okay, and what is that is, we'll see what actually the meaning of polyamides. Okay, so let me write that first. If you have the repeating units, if repeating units are joined or linked by bond CONH bond, okay, and this bond we call it as amide bond. Remember that. Okay, if repeating units are linked by amide bond, and that we call it as the polyamide, and this is the joining. Okay, two repeating units are linked by this particular CONH, and remember this is the very simple form what I have written, and actually it is C double bond O and NH, the bond will continue. Okay, in simple manner we can write CONH, and this we call it as amide bond, and one more name is peptide bond, but usually in the chapter called polymer we are supposed to use the word called amide. Okay, amide bond, CONH bond we have. Okay, and we have very well known examples for this, that will be polyamide, and I am going to write here the examples for that. The one example is nylon 6. Okay, and one more example I am going to consider, that will be nylon 6,6. So these two polymers, okay, so what are those? Nylon 6 and nylon 6,6. These are the polymers that belongs to polyamide. Why? What is the reason behind that? Because in the partial structure of nylon 6 and nylon 6s, we are going to see CONH bond, that will be the amide bond. So if we see the amide bond, and that belongs to a class called polyamides. We try to know about that. Similarly, we'll see one more, that will be polyesters or polysters. And in this case, if the repeating units are joined by, if they are joined or linked by ester bond, if they are joined by ester bond, what is that actually? C double O bond, that is actually the ester bond, and that we call it as what actually the polyamide it is. Okay, and in complete sense I am going to write, this will be like this, C double bond O, and this is how actually the open structure I can consider, and that belongs to, we call it as the polyester. And one very well known example I will write here, that will be terylene. Okay, and one more name we have for that, and that is Dacron. Terylene or Dacron belongs to polyester. Why? Because in the partial structure of a terylene or Dacron, we are going to observe that the repeating units are linked by the ester linkage or ester bond, CO bond, and that's why, and that belongs to polyester, and this particular nylon 6 and nylon 6,6 belongs to polyamide. And in the previous year competitive examination, many times the same concept has been repeated, polyamide, and which of the following is polyamide, which of the following is a polyester. So try to know, and these nylon 6, nylon 6,6 polyamides, and terylene, Dacron, polyester. Okay, one more concept I am going to add, these two belongs to condensation polymerization. Know that one. These two headings, that is polyamide and polyester, or you can say nylon 6, nylon 66, terylene or Dacron, and all these belongs to condensation polymerization, since there is elimination of simple molecule like water and bifunctional, trifunctional monomers we are going to observe. So now I am going to talk about the structures of nylon 6, nylon 66 and terylene or Dacron. So now I will come to the next example, that will be ninth one, and the ninth one I am going to consider what is that actually, nylon 6 I am going to consider. And now I hope you can guess, nylon 6 belongs to polyamide, since we have CONH bond. Remember that is a fiber also. Nylon 6, nylon 66 both are fibers, both are synthetic polymers. Okay, so try to know about that. And now we will see what would be the structure and the monomer of that one. Okay, so now I am going to draw the structure of the monomer of N. Okay, and the name of this monomer we call it as caprolactam. Try to know that one. This is caprolactam. These corners 1, 2, 3, 4, 5, the corners, these are actually CH2 groups. You can write CH2 groups, or in very simple way you can show here, and here we have NH, and actually this is a C double bond O, and that is actually the structure of caprolactam, and large amount of N we have. Okay, and one special condition we have in this particular example, we are supposed to heat the caprolactam. Try to know, this is a special case. Nylon 6, we have to heat the caprolactam in the presence of water. Okay, in the presence of water we have to heat this caprolactam, and we are going to get the structure, and that will be nylon 6 here. Okay, and actually in this particular example, and I cannot show you how the water is going to be eliminated and how does it is going to be linked here, since it is complex structure. Directly the partial structure I am going to write here, and the partial structure will be, and I am going to write C double bond O, okay, and CH2 5 times we have NH, and this is the bond continues, and the brackets I will write here, and I will write N, and that will be what actually nylon 6 we have. So the statement how we are supposed to write, nylon 6 is formed by condensation polymerization of caprolactam just by heating in presence of water we have. And one more concept you remember, why we got the name as the nylon 6 itself here. This 6 indicates the number of carbon actually. Okay, so how many carbons we have? 5, and here one more 6, so 6 carbons we have, therefore we got the name called nylon 6. And remember that is a fiber, that is a synthetic polymer, and that is also what actually polyamide, since we have CONH bond linkage, and that will continue. Okay, and that is how we can consider the structure of nylon 6, which belongs to a class called polyamides. One more example of polyamide we'll see now, and that is nylon 66. I explained this nylon 66 while explaining the concept called condensation polymerization. We'll repeat that one, it is quite important one. I think the example is 10, okay, and that would be nylon -6, 6. You should say it as 66 only, and you should not spell it as 66. I will tell you later why it is called nylon 66 only. So we'll see the monomers of a nylon 66, and remember nylon 66 belongs to condensation polymerization, polyamides also, synthetic polymer also, fibers also this is. Okay, and the monomers are, okay, so let me write here first. The first one is hexamethylene diamine, hexamethylene diamine, and one more is adipic acid, adipic acid, hexamethylene diamine, methylene, okay, and CH2 methylene, hexa CH2 6 times, diamine, therefore bond NH2 and bond NH2. This is a monomer, n number of difunctional monomer it is, and we can guess this would be belongs to condensation polymerization. Adipic acid CH2, 4 times we have, here we have COOH and here we have COOH. That will be the two monomers of nylon 6,6. Okay, and one point I want to highlight in this case, because usually in the PVC examination the question we have is name the monomers of nylon 6,6, 2 marks. I repeat the question, name the monomers of nylon 6,6. Try to understand the question, they asked the name, not the structure. So in that case you should write hexamethylene diamine and adipic acid. You are going to get 2 marks for that one. If they ask draw the partial structure of nylon 6,6, only draw the partial structure, no need to write the entire reaction and statement along with that. If they ask explain the preparation or manufacture of nylon 6,6, then you need to write the all thing what I used to write on the board. So now if these two undergoes a kind of polymerization, that will be condensation polymerization. I told you there is elimination of water, and you can mention here also this belongs to condensation polymerization, and usually the high temperature and high pressure you are supposed to consider, and water is going to be eliminated. Okay, and here OH from this adipic acid and 1H from this hexamethylene diamine, water is going to be eliminated. Similarly from left side also and right side also the water is going to be eliminated. So therefore n number of monomers we have, and therefore n amount of water is going to be eliminated. From here first 1H is going to be eliminated, from right hand side OH is going to be eliminated. I hope now it is clear to you how we can guess what would be the structure of that one. So water is going to be eliminated here, and H from the left side and OH from the right side. So now we'll join and we'll eliminate water and we'll try to write the partial structure. So what I'm going to get here is bond NH we have, okay, and CH2 6 times, then 1H is removed, therefore NH we have, OH is removed, CO, or you can write OC the same thing, and we have what actually CH2 4 times, and OH is removed, CO, and the bond we have, and the braces with the subscript N, and what is this actually? That will be nylon 6,6. And if you observe, see, in the middle we have NHCO bond, and in any partial structure if we have NHCO bond, and that belongs to polyamide, therefore nylon 6,6 belongs to polyamide, and that is an example for condensation polymerization, since there is elimination of simple molecule like water, and bifunctional monomers we have here, also bifunctional monomers we have here, and this is the partial structure of that one. We got the name nylon 6,6 because, so these two 6 belongs, this 6 belongs number of carbons in one monomer, and this 6 belongs to number of carbons in one more monomer. In case of hexamethylene diamine, carbon we have 6, therefore this 6 stands for that. In adipic acid, 4 carbons in the center, this one carbon and this one carbon, totally 6 carbons, and that is the name we have, why it is called nylon 6,6, and these two belongs the number of carbons present in the monomer of that one, and that would be the entire structure, the reaction of nylon 6,6. The statement is nylon 6,6 is formed by condensation polymerization of hexamethylene diamine and adipic acid at high temperature and high pressure, and that would be the statement what we can write for nylon 6,6. Remember, that is the best example for condensation polymerization and polyamide. We'll see one more example, and the name I have given you already, that will be terylene. Okay, remember terylene, you can call it as the Dacron. Two names we have, I use the both. In the examination they may use any one, terylene or Dacron. And if you just recall what I told you, terylene and Dacron is the best example for polysters. Okay, so what is polyester? The repeating units are joined by a kind of bond, we call it as ester bond, bond COO bond, and that we call it as ester. And now we'll see how we are supposed to write the monomers and partial structure of that one. Remember, terylene is also an example for condensation polymer, means there should be elimination of simple molecules like water. So we'll see how about the structures for that one. CH2 and OH, and here we have OH. This is the one monomer. Okay, and the name of this monomer is ethylene glycol. See, ethylene glycol, or you can say simply glycol, or this is ethane 1,2-diol. So two alcoholic groups we have. This is a glycol actually, and a large number of this monomer we have, and it has a bifunctional monomer. You try to know, that indicates that this undergoes condensation polymerization. And one more is benzene ring with para dicarboxylic acid. So these COOH, they are present in a para position to each other. Okay, so benzene we have, and we have a diparacarboxylic acid structure, and you can call it as terphthalic acid. The name is terphthalic acid or benzene diparacarboxylic acid, you can call it as. Usually the preferred word is terphthalic acid, and we have the two functional groups we have again, and this undergoes a kind of polymerization, and we can guess the kind of polymerization is condensation polymerization, since we have two functional groups we have in the structures of the monomers, and there is elimination of water, and I told you that when there is a n amount of elimination of water, and how water is going to be eliminated. Okay, see here, OH from terphthalic acid and H from ethylene glycol. Similarly, left side, right side has to be eliminated. So H from the left side and OH from the right side, as same as the previous one what we did. And now I am going to write the partial structure of that one. Here I have O, okay, and CH2, CH2. Okay, so write what we have here. We have O and C, one O and one more O and C, and we have the benzene ring, and again here we have only CO, and the bond will continue. Okay, and place the braces or brackets and write N, and that would be what actually terylene you can call it as, and one more, the name will be Dacron, you can say terylene or Dacron we have. Okay, so this is how we can write the structure of condensation polymerization polyester terylene. So just you observe here, the linkage will be COO. Okay, and if we have a CO linkage, and that we call it as ester linkage, and the polymer we call it as polyester. Okay, that's why terylene or Dacron belongs to a kind of polymer, and that we call it as a polyester. Okay, and I told you one concept, that the polyester can be defined as, I told you that what is actually the repeating units are linked by ester bond, and such kind of polymer we call it as polyester. One more we have. Okay, what is that? I am going to explain here. Polycondensation of, okay, so polycondensation of diols, and one more is dicarboxylic acids, diols and dicarboxylic acid. If there is condensation, if there is polycondensation of diols and dicarboxylic acid, diols, two alcoholic groups we should have, dicarboxylic acid, two carboxylic acid function group we have. And now if you remember the structure, you can guess, since we have two alcoholic groups, therefore this is a diol, and since it is two carboxylic acid groups we have, this is a dicarboxylic acid. Remember, if we have a diol and a dicarboxylic acid, definitely you are going to get what actually the polyester. Okay, so polyester can be defined as the polymer which we are going to get by polycondensation of the products of diols and dicarboxylic acid, and that is the best example we can give it forward, actually the terylene or Dacron we have. Okay, and that is also a kind of very hard and tough substance. It is, we are going to use in a n number of fields this particular terylene on Dacron, and that would be what actually nylon 66. Remember, if they ask the question that name the monomers of terylene or Dacron, and what your answer should be ethylene glycol and terphthalic acid. Draw the partial structure of Dacron, draw only the partial structure. Okay, and remember, again I repeat, in a partial structure the bond should extend from left side and right side, and brackets you should write and n you should write. If you make any mistake in just by leaving this n or extending the bond, you have the chances of losing marks here. And remember, you need to write n. Sorry, I have not written n here. It is compulsory. It is compulsory to write the n, because one can easily guess that if you have a one monomer and two monomer, you cannot get the polymer unless you have what actually the large number of monomers we have, then only you are going to get the polymer. That is the basic thing you should know, how to draw in a correct manner of the polymer structure here. Again, if you are not quite good in the partial structure, you need to check the valency of carbon. Sometimes it happens, if you just miss any one hydrogen and think over it, you are going to lose 1 marks for that one, because the carbon that should be tetravalent nature only. And that is about, the two polymers what I explained, that is the nylon 66 and one more is the terylene or Dacron. Some other examples also we have, and that we'll discuss in the next session. Thanks for watching.